Hello, welcome to this Learn tutorial on subnet masks. So what is a subnet mask? Well, when computers are sending data from one computer to another, either on the same network or over the internet, then it sends and receives it using IP addresses. And IP addresses are broken up into two components. You have the first part, which is the network ID, which in this particular case is 192.168.0. And then the second part is the host ID within that network. So, which is fine, which is good, but we've got a bit of a problem in that we don't always know, well, where exactly out of all of here, where does the host ID actually start and where does the network ID end? Because if you think about it, we could have maybe the first two numbers are the network ID and the last two are the host ID. Or is it the first three numbers and just the last one is the host ID? Or is it just the first one and the last three are all the host ID? Well, we don't actually know just looking at the address itself, which is what a subnet mask is. A subnet mask is a way of identifying where the network ID ends and where the host ID begins, so that we know which bit is the network and which bit is the host. Now, why do we need that? Well, when we're sending data between computers, well, there's three possibilities. Either you're sending it to somewhere on the same network, in which case you just want to send it directly to that recipient via the switch, which is fine. But if it's on a different network, you need to do something completely different. You can't just send it directly to them. You need to send it off to the other network, and it often via different networks, and you send it via the gateway and the router, and then it disappears off to a different network. So these two packets, these two pieces of data, depending on the IP address and depending whether it's in the same network or the different network, they're going to go to different locations. They're going to follow different paths until they get there. Also, as well, obviously, the third possibility is that the address doesn't exist. So if it doesn't exist and it's on the same network, well, that should be quite easy because you can see if you can find it, see if you can, see if the switch has got the IP address logged. But if it's on a different network, you won't really know if it exists or otherwise. You'll just have to send it off to that network, and that network can decide whether it exists. So we do need to know which bit is the host and which bit is the network, because it's going to go to different places. Okay, so let's have a look how this works. How do we tell the computer that this part is the network and this part is the host part? Well, what we do is when we break it up, quite simply, we apply a mask. And the mask, say, for instance, there's our IP address there. What we do is, if we convert our IP address into binary, which makes a little bit more sense because that's what computers use, what we do is we apply a mask of ones and zeros. And it's really, really simple. The bit that we want to say is the network, we put all in ones in the mask. And the bit that we want to say is the host part, we put all in zeros. Okay, and so the first 3 bytes here, 8 bits, 8 bits, 8 bits, 24 bits in total are masked in a 1, and the remaining 8 are in zeros. Now when we're writing this down as IT people or computer scientists, then we've got two different ways of writing this down. The easiest way is and it's the newer way, is the /24, which literally just means the first 24 bits of the mask are ones, and whatever's left is going to be zeros. Or the old way of doing it is we actually write down the denary conversion of all of these ones. So this first byte would be 255, this byte would be 255, this byte would be 255, and the final byte would be 0. So both of these mean that a 24-bit mask. So let's have a look. So let's just see, there we go. So let's see that in action. So the network mask, we apply it and we get the network ID that comes out at the other end. So what has happened here? Well, it's quite simple really. All you do is you take the IP address that you've converted into binary and you do a logical AND with the network mask. Whoa, logical and. Well, what does that mean? Well, it means that anything that was a 1 here, so 1 and 1 goes to 1, 1 and 0 goes to 0, and 0 and 0 goes to 0. Which sounds pretty complicated, but actually, in reality, what it really means is that all of the network part of the IP address here stays exactly the same. So that doesn't change. The blue bit stays exactly the same. You write all that down as normal. All of the host part gets changed to zeros. So all that you've got left really is the information about the network part, which is why it masks off this bit here. It just hides all those bits. And that's really, really useful. So if you've got two computers, all they do is you've got the sender and the recipient. The sender masks its own IP to work out what its network ID address is, and then it masks the IP address of the recipient. And if those two masked addresses are the same, then you know you're on the same network. And if those two masked addresses are different, then you know you're on different networks, because this part of it here, the network part of it, is different. We're just ignoring the host ID part. There we go. And you can just convert the network ID here at the end back into DINA if you want to. I sometimes find it's easier just to leave it in binary. But on exams and quizzes and stuff, you might be asked to convert it back to denary, in which case you just convert the final amount back to denary. That's a decimal. Okay, so we're going to walk through a few examples and look how it works. But before we do that, let's have a chat about home networks, or even home office networks, or just small office networks. So let's say a home network. You have a router, you have a switch, maybe, you have some devices that are connected. In your average home, you maybe have, well, here we've got 4, but you probably have about 10, 15 devices in a home network and a printer and stuff. In a home network, in a standard home network, you can have up to 254 devices, and we'll see why that is in a bit. But standard, usually you just have a few. You've got a printer that you want everybody to be able to share access to, and you might want to be able to share files between computers so that each computer can access the other one as well. So that's pretty standard, that's okay. But that might not always be the case. So for instance, if you're working in an office environment and you want to separate each department, so you might have 2 or 3 or 4 departments, you might not want each department to share each other's resources. They might not be happy about the other departments using their printer. Or some departments might have sensitive data on their computers, so therefore you want to block other people from those parts of the network, even though they're part of the same organization. And this can be done, I'll just show you the example of a home network, but this can be achieved in a couple of ways. First of all, what you could do is you could physically split the network up. You could have a separate router, switch if you need it, and separate internet access, which is okay, and that would work. And you could keep them like that. But that's quite expensive and also quite difficult to maintain. You've got to buy and maintain a router, a switch, and a separate internet access. So there is another way of doing that rather than physically splitting the network. And what we can do instead of physically splitting the network is we can logically split the network through the use of a subnet mask. And what this subnet mask does is it takes the original 255 IP addresses that we've got available and it splits it into 2 smaller networks. So 256 divided by 2 would mean that there would be 128 IP addresses within this subnet here and 120 IP addresses available within this subnet here, or thereabouts. I'm going to talk about it in a minute. So we can do this entirely through our network configuration rather than having to buy extra hardware, and this is known as subnetting, and it's where subnet masks come in. You can see here I've got the 255, 255, 128. It's a different, I've actually changed the subnet from the default subnet that you'd have on a home router to show you this is how you'd split it up. And we'll look at how that works. So that 255, 255, 255, 128, that can be written in shorthand just using a 25/25, and that means that it is a 25-bit mask, one more bit than before. So your standard mask for a home network is a 24-bit mask. What we're going to do now is we're going to change the mask to a 25, and that's going to do a few interesting things. So here you can see what we're going to do. Here's our IP address that we've written in binary. And now what's happening is instead of 24 bits here that are part of the network, we've got this extra last bit taken from the end. And I'm going to do that with both our IP addresses. And what I've deliberately done here is I've chosen a low IP address number here and a high IP address number here. I didn't have to choose 229. I'd probably chosen something smaller, but I just thought that was somewhere near. So that will definitely work. So we take the mask and we apply the logical mask, which effectively just erases and replaces all of the host components with zeros, which produces a network ID. The first network ID is the same as before. So because this is such a low number, it's just sat within the same network as before, the ID. But interestingly, this one here with the higher number, because we've taken this last bit as to be part of the network, now what happens is the network ID of this IP address here is 128 at the end, not 0. And that's because we've kept this final 1 here because of the extra 1 in our mask when we applied the logical AND. So we've subnetted our network. Now these two IP addresses are not in the same not in the same network, and therefore the two computers can't communicate with each other. And if you put the printer here with a similar high IP address there, then this computer here would not be able to communicate with the printer because it's on a different network. This one is on subnet ID 0 because it's there. That's the extra one that we've just added here. That 0 corresponds to that 0. This is on subnet 1. The computer doesn't really care about that, but we logically would need to think about it like that. And one last point is that we've only got 126 hosts in each of these subnets. And the reason being is that of the 128 available addresses, 2 of those addresses are reserved. The very first of each network, very first available address in each network is reserved, and the very last address is also reserved. The first address, which is the network IP address, the network ID followed by all zeros, which will be the first one, which is all of this bit here, but just that bit with zeros. That is the network IP itself. So that's the IP address of the actual network, not the IP address of any devices on the network, just the IP of the actual network itself. So that's, and the way you work that out, if you're asked to do that in an exam or a quiz, is you just keep all of the bits from the network component and then just replace all the host bits with zeros, exactly as the same as you did with the mask. And the other thing that gets reserved is the broadcast address. And this is very, very similar in that all of the first part stays the same, but you replace all of the end ones with ones. So whereas this replaces it all with zeros, this one replaces it all with ones. Do that, and then you can calculate it. You can just transfer this back into denary, and that will get you the broadcast address for that subnet. The reason we need to reserve that broadcast address is because as soon as a computer actually connects to a network, it doesn't have an IP address. And because of that, it needs to get an IP address, but it needs to listen on an address in order to receive the data. When it fires through a request and the DHCP handler sends back the IP address that it can use, it needs to have some address that it listens on, otherwise that will never get sent through. So it listens on the last address, always on the final available IP address is available. So it's really useful, that broadcast IP. So you can see these two aren't on the same network, so they can't communicate. So that's how you break it into 2 subnets from the original network. And you can do this with 2, or if you want to, you can do it with 4 subnets. So with 4, exactly the same procedure, but instead of doing a /25 subnet mask, you just do a /26. So you basically reserving 2 digits for the subnet, and only 6 are left for the host ID, which will give you 4 subnets, because you've got 00 or 01 or 10 or 11. 4 different subnets, and then all the host IDs that are available for each one. There'll be 64 IP addresses, which will make it 62 hosts available in each. And let's have a look at that. So there's a quick example. So you can see we've got the same IP address as before for each one, but this time we've got a /26 mask, and there you can see the IP there in binary, and you can see that only the last 6 digits now are reserved for the IP address, and that changes quite a bit. The mask changes by 1 because we're masking over even more, which means that the network ID can change as well. Again, the first one, it doesn't change because this keeps falling within that first subnet, which it keeps the same network ID, but this one now has changed again. It's gone from 128 at the end to 192, and the reason being is that it's kept, instead of just keeping this 1 digit here, it's now got both of those digits here to be added into the overall network ID. So it's changed. In fact, actually, the 4 subnets, the network ID for each would be 192.168.0.0, 192.168.0.64, 192.168.0.128, and the final one there at 192. And you can see the subnet ID because we saw those before. This one has got 11 as its subnet ID. You might be asked that in an exam as well. What's the subnet ID? And your broadcast address again changes for both, I think. Certainly changes for this one because now the last available IP address within the first quarter is going to be IP address 63 at the end because it's moved along, and this one stays the same. There we go. So that's pretty much all that we need to cover all the way through. So what it is worthwhile noting as well that noting that you don't have to keep going this way. You don't have to keep creating a longer subnet if you don't want to. You can go the other way. So in large organizations, they might want to put 1,000 or 2,000 or 5,000 devices all on the same subnet. And that can be done. All you do is you just change the mask. You change it from a 255 mask or a /24, which is the easier way of writing it, and just change it to a /23 mask, which will mean that now you've got double the number of hosts double the number of IP addresses that you could before per subnet. You have 500 IPs or over 500 in a subnet, and you can keep going as big as is available. So depending on the class of depending on the IP address that you're using. So here you can go. They have done it up to over 1,000 IP addresses per subnet, which is quite large. Whilst you can keep theoretically going higher and higher and higher, for a standard network, it's not really a good idea because the more hosts that you can put inside of a subnet, that means there are the more hosts that are broadcasting on that broadcast address, which means that the whole subnet gets busier and busier with broadcasts and with traffic. And if you have a huge amount of hosts and they all connect together and they all try to broadcast and they're all stuck on the broadcast because no one can receive because we're waiting for all these broadcasts to sort themselves out, you end up with what's known as a broadcast storm, and the whole network can slow down. So it's generally not a good idea to making network subnets too large. Okay, so we've just got one last thing to cover now, and that is network classes. Technically, they're no longer used. So since 1993, we have now have a classless system. But back before then, you were limited to what network masks you could actually do, and some of the names, because they're pretty standard, have stuck. So we'll talk about that now. So when the internet was first invented, you had a limited choice when it came to network masks. You only really had a Class A or a Class B or Class C mask that was available. So the Class A mask is an 8-bit mask with 24 bits reserved for the hosts. Class B mask would be a 16-bit mask with 16 bits reserved for the host. And the Class C mask, which is 24 bits with 8 for the host. This is still quite commonly referred to, especially with home networks or small offices. If someone's talking about what network mask is on there, they can just say, oh yes, it's a Class C mask. And people will know that that's a 24-bit mask. There you go. So it's just to be aware. You might get asked exam questions where they'll have, apply a Class C mask to this IP or something like that. So you just got to be aware of the terminology, although they're not technically still used. Okay, so that's it. That's the tutorial over. I will put a copy of this slideshow on my links, so you can use that. You can work through the slideshow if you want to, if you need to use it yourself. If you do have any comments or questions, just drop me a comment on the YouTube video. And if you want to like and subscribe, please do. Okay, thank you very much and good luck.